Hey guys, welcome to a very special Supreme Podcast episode. Today we have me and Akshay, the two dumbest people in crypto, talking to some of the smartest brains in crypto about what the way forward should be for the whole industry. Akshay, why don't you introduce our guests?
Awesome. It's great to be here. Tanmay, speak for yourself. But I think that's a fair statement. I'm incredibly intimidated at the beginning of this episode, so I hope we get to play the role of the audience that's watching. As our first guest that I'm going to introduce is going to moderate. Welcome, C-Node. Connor works on the Switchboard protocol, and we're very excited to have him moderate this. Thank you for agreeing to do this, C-Node.
Thank you. Thank you so much.
And with that, we also have the two wonderful panelists who are going to debate it out on what the scope and architectural trade-offs in achieving effective decentralization should be. Welcome, Anatoly, co-founder of Solana and CEO of Solana Labs.
Awesome to be here. Thank you.
And welcome, Toghrul, a researcher at Scroll, which is a ZK rollup on Ethereum.
Thanks for having me.
Gentlemen, it's a pleasure to have you. With that, we will now yield the floor to C-Node to kickstart this conversation.
Okay, thank you. I'm a huge fan of Solana and of Scroll. I'm honored that Akshay and Super Team invited me to come and moderate this discussion between two builders who have blown our minds with their work and in many Twitter conversations so many times. I thought it might be good to start it off on a lighthearted note by asking if you two could make a good faith elevator pitch for each other's projects. We can start with the wartime OSS maintainer himself, and then we'll switch off who starts on each question.
I think zero knowledge proofs are magic in the sense that they do something that blew my mind. Me as an engineer, when I first kind of started thinking about them and like understood the basic principles of it, it felt like one of those like floodgate opening moments. And I think it's awesome. Like I think all the research that folks are doing in this is like super important, and like I can't wait to see it like work in practical applications. So I'm super excited to see like all the progress you guys are making.
My turn, I guess. I mean, the first thing that comes to mind is parallel execution is fantastic. I mean, I guess if you really want to scale blockchains and scale decentralized execution, you need to parallelize execution, and Solana achieves it. Another thing that Solana does great is it maximizes the throughput. It basically assumes that you can interact with the blockchain at the lowest possible latency that is tolerable by any distributed system.
It's the most wholesome beginning to a debate I've ever seen, by the way. I love it.
Yeah.
It's amazing when you take crypto Twitter to a podcast, things get so much better.
I don't think I think we're actually like mostly agreeing just about everything anyways.
We're hoping for some fireworks, Totally.
Yeah.
We'll do one more fluff question before we get into the technical stuff that everybody is here for.
Are we going to build a trustless bridge?
Yes, we are going to build a trustless bridge. Okay, so what is the purpose of the technology we are developing? Why should engineers and researchers work on improving public blockchains? We'll start with Toghrul.
I think for me, the reason why I'm in this space and the reason why this entire technology excites me is the fact that you can build applications that are censorship resistant, especially for people who grew up in countries and places that are not the most democratic and don't really have free speech. That's something that allows them to basically express themselves and interact with things online without some overlord dictating what they should do. And that's not only limited to those countries. For example, with the recent Tornado Cash situation, it demonstrates how much censorship resistance is important and how we can essentially be completely disintermediated from a ruling of a single country or a single group of people that are powerful.
For me, I always thought that like the coolest thing that was actually built is self-custody and the ability for humans to use cryptography. Even like going beyond self-custody, just the idea that like an individual now has very consumer grade cryptography, they can sign signatures and they can transmit them. That was really, really hard to do before Bitcoin. I don't know if you ever like worked at a big company, but like for me, like getting a piece of firmware signed at Qualcomm was like a year-long process. Binance signs like a billion things a day. Like every Solana user signs like a bunch of things per day. It became like a very simple thing to manage your own signatures. Even though PGP and all these other cryptographic private key, like PKI technologies existed, they were super clunky. But now this like idea of messing around with tokens, with NFTs, made it a consumer grade application. People built the tech to make it easy. And I think the really powerful thing about it is that it's a very powerful tool in the hands of individuals. And when you have a lot of them together, they can coordinate through these distributed systems. And that's like, I think the really cool thing is, right now, I don't know, maybe it's like 1 million people per day that actually use all these chains combined. It's a very small number of humans. Imagine 100 million people or 1 billion people that are all just have the power to do this. They go online, they all like collectively decide we're going to like make this meme happen, or we're going to take this action, and they transfer the money to do that, and then it automatically executes, and like the world changes like that. It's a very scary, powerful tool, and I think is going to tremendously change the world for the better. So I'm pretty stoked just about that very simple thing, getting humans to coordinate with cryptography.
Very cool. Very cool. Sounds like we're somewhat in agreement so far. Let's forget about light clients for a moment. How big should a full node be? We'll start with Toghrul.
Big. What does big mean?
System requirements, hardware requirements, bandwidth.
Well, it should be as small as possible for the task that it's doing. And the task that it's doing should be delivering some value to the world. So to like be useful to humans. So if there's like a bunch of humans that need these nodes to be bigger, then they'll be bigger. If there's not enough humans using these things and the nodes are smaller, they should be as small as possible, right? Like engineers are going to like go look at a system and be like, okay, well, the current demand is X, and we're not like utilizing the hardware, so let's just cut it down and make it simpler and cheaper. Like I guess we always think of it internally as like just improve like the actual usability of the chain, like make it more useful to humans. And like part of that is increasing capacity. Capacity does not mean the node has to be bigger. It's just the software can expand to use more hardware. And as soon as people start using so much of it that the hardware needs to grow, then the hardware grows. That's great. Like that's like a huge relief. That means that like somebody somewhere in the world figured out something useful to do with this thing.
But you would never limit the capacity to keep the size down. Is that correct?
Yeah, I don't think we would ever limit the capacity of the system and like push away useful like users to keep the size down.
Sino, do you think you could articulate the issue at hand here, which is why node size matters, and just the philosophical two sides of the debate before we, maybe have Toghrul, because many of our folks may not be familiar?
Oh, sure. There's one school of thought which says that the full nodes should be as big as they need to be to handle all the capacity that the users are creating. And then there's sort of another school of thought which says the size of the full node is what we're solving for. We need to have a target hardware for the full node. And if that means we can't support as much capacity as possible, or we need to raise fees for this scarce resources of the network, then we'll just let it happen, basically. But maybe Toghrul could explain it better.
I mean, you explained it quite well, but I'll just add one thing. So I tend to differentiate between full nodes and consensus nodes. So a full node is a client implementation that can fully verify the chain and its history and all the transactions that are included in the canonical chain. Whereas a consensus node on top of that also participates in the consensus. And then, especially that's true for Ethereum, within the consensus, there can be different types of nodes. So for example, in Ethereum, we have a concept of builders, which are resource heavy nodes that construct the blocks and can be as big in terms of hardware requirements as required. And then there are validator nodes that are just standard nodes that can even run on, let's say, Raspberry Pi. So I think for the validators and for the full nodes, from my line of thinking, the requirements should be, the hardware requirements should be as low as possible. So essentially, as many people as possible should have the ability to validate the chain fully.
I think the question is, would you set a cap on the hardware saying it needs to be below the spec no matter what? And then you design the system around that cap? Or because Solana's philosophy is also hardware should be as cheap as possible because it's just stupid to waste it. Right?
I get that point.
Yeah.
No, I get that point. My point, from Solana's perspective, it's a bit different because what you're saying is you should minimize the hardware, but if the requirement, the bandwidth requirements or the throughput requirements are greater than what the hardware allows, then you should increase the hardware requirements. Whereas I think from Ethereum's perspective, and what I agree with is with the philosophical argument that there should be a certain cap. It can change from time to time. So let's say, obviously, if you set a cap 10 years ago, the hardware has changed drastically within 10 years. So you have to upgrade that cap once in a while, but it can't be demand-based. It should be more like, what's the current state of the hardware and accessibility of it, and let's change the hardware requirements in accordance to the accessibility of that hardware.
I have a follow-up question on what you said about proposer-builder separation, which is like a new emerging idea in the ETH scaling roadmap. You mentioned that the builders have very high system requirements and that the proposers have much lower system requirements, and you said they could even run on a Raspberry Pi. What are the builders doing that requires so much load, and how can the proposers be so light if they have to verify these blocks that are being built?
So currently, the main job that the builders are doing are constructing the blocks and including all the search and transactions bundles that are propagated to them. But once proto-dank sharding and dank sharding are enabled, another job that the builders are going to have is computing the KZG commitments, which are not very efficient to compute. And so it's not really a problem with proto-dank sharding, but especially with dank sharding, it's going to become a problem because you're going to need to compute a lot of KZG commitments per block, and that would basically require quite an impressive setup to do, and therefore the requirements will drastically increase.
Once we have full dank sharding and proposer-builder separation, are the proposers no longer going to be responsible for storing or at least tracking the full state for a block?
So they have an option to subscribe to the entire block, but by default, they only need to store a portion of the block. So I think out of 256 channels, you only need to store 32, something like that, for the block transactions. You still need to store the parts of the block that are responsible for the execution, but because block transactions are not really accessible by the EVM, you don't need them. You just need their commitments.
Which node computes like the state root in this system?
It would be a builder, but assuming that you have a KZG commitment, proposer or any full node can also compute that state tree. You don't need the block transactions for that.
But like before a consensus node, the validator votes, somebody needs to compute like the thing they're voting on, right? So my understanding was that the validators are connected to like basically a geth or whatever, something that's actually doing the execution. What is the executing node called?
Initially the block is constructed by the builder, but the proposer can also construct the block is just super expensive to compute the KZG commitments, but you don't need the KZG, the blob transactions themselves to compute the proof.
Got it.
So I have a question for the both of you. It seems like, Toghrul, you suggest that everybody who can have a smartphone should essentially be able to run a node. And is the end state that every human with a smartphone should be able to validate all transactions? Or is there like at some point where the benefit of decentralization starts to sort of like taper off and it comes at the great cost of some other things like performance? I mean, for the both of you, I don't know if you have a view on that.
So like it's kind of, you have to kind of analyze this a bit more concretely. Let's say you have this like software running on your phone and all the other instances of Ethereum nodes, all the other state is destroyed. How much of the state can your software recover? Like the proposals that I've seen for the things that are running on phones, basically zero, because you have just a few pieces of the erasure codes that give you like some data of the chain, but nothing, you can't really construct anything. Then you're saying, okay, maybe enough of these phone nodes survive that you can't construct the entire data, but still somebody has to go recompile it into the actual chain and then execute it and say, look, we recovered the state, now we're good to go. That's like a fine security assumption to build for. And that's okay, but it still relies on one honest validator to participate in that network. So that one node that's going to decide to reconstruct all the state and say, okay, I'm the one honest node. Ta-da, here we are.
There's no way to escape the need for someone to have the whole state.
Yep. And that is, I think, been like kind of when I started working on these systems, I did not consider this 1/n assumption as a possibility. And it kind of like the research on Ethereum 2 is like kind of was one of those again, oh wow, there's like a different way to look at security. And that's a much, much stronger assumption than what most people, when they say trustless and they say that you have a trustless bridge, they are talking about honest majority assumptions that as long as most of the network is honest, most of the full nodes, which means the vast majority of them, 66 out of 100 or whatever, as long as those are honest, then the network has survived. But this improvement going to these like light nodes and this 1/n thing is a much, much stronger security assumption because you only have 1/n. And this is something that Solana actually like depends on. We need 1/n assumptions, and that's why we need these at least one honest node in the network. And this is something that I talk about all the time. And that one honest node cannot, I don't think, ever be on a phone realistically. Maybe as an experiment, you can probably in a phone 10 years from now, you can get it to run. But usually for practical purposes, it needs to be a highly available system that is connected to the network and is constantly reconstructing the state and monitoring it and flags that the network did something wrong as soon as possible. And that's not something that you can do on a mobile device that goes in and out of range, right? Drops connection, is not constantly like connected to a bajillion things. Maybe you can take that piece of hardware and stick it in like a server rack and do the same thing with it. You need a high availability system that's dedicated for it. And with that premise, this is what Solana is then, okay, given that thing needs to exist, Solana can maintain the same security properties just with very expensive versions of those. And the one thing that we don't want to sacrifice is a different use case than Ethereum, which is like Ethereum is awesome. It's doing its own thing. It's trying to minimize the cost of everything. But there's a very important thing that these systems provide, which is in propagating information around the world. It's when something happens that's important to markets, important to finance, that data has to travel from wherever it happened to New York Stock Exchange. And that information propagation is money. Like if you ever traded, that's very, very important. That latency is important. The capacity of how much that can propagate is important. And our goal is to make sure that like everyone in the world can receive this data at the speed of light as fast as possible. So that actually means that we can't put a cap on the hardware. Like we actually have to like increase the hardware spec to whatever the demand is for valuable information to propagate through the network. We can't split the quorum. We can't shard. We can't store parts of the data, right? And move and do like these tricks that are, I think, very, very cool. But if you have that constraint, you're trying to solve for that, like, let's build a global synchronization engine for every bit that has market value in the world. You have to actually like build the system to meet the capacity. So that trade-off for security is for the price of the nodes, but it's not a trade-off for security. And this is kind of the point that I'd like to drive home, is that you still have this one honest node on Solana, just like you have a one honest node on Ethereum that's required when all of these super cheap nodes come together and reassemble a state. Both of them have that one requirement. There's at least one honest node that says, hey, something went wrong.
From my perspective, so short answer, no. I don't think it's viable for users to run full nodes on their phones. The throughput requirements are too much to realistically run a full node. I think I meant more like stationary devices like laptops or realistically PCs or Raspberry Pis, something that you wouldn't be moving around all the time with. With regards to the 1 out of n assumption, so there are a few things there. So 1 out of n assumption is enough if you know the canonical chain and want to recover the history. But if you want to catch an invalid state transition, for example, you need to maximize the probability of that being code. You need as many full nodes as possible. So the more nodes you have, the bigger the probability of catching an invalid state transition. Another thing is, for example, in a scenario where, let's say, an attacker destroys all but one node and constructs an alternative chain that is historically not canonical, but it presents it as canonical, one node is not enough to recover the canonical chain, because if my 100 nodes, I'm an attacker, present to you an alternative history that looks better just because I constructed a longer chain, for example, and you present a shorter history, which is actually the correct history, all the outsiders will accept my history.
There is no correctness at that point. What's important is that like a client that is not eclipsed and can see the one honest node and the 100 you call attacking nodes, that they see that there's a conflict, that they don't accept confirmations until it's resolved. So as soon as this like alternative history exists, there is no true chain anymore. What's important is that clients that are processing confirmations and accepting like value transfer, they just say, hey, it looks like there's a double vote. It looks like there's two forks now. We're just going to not accept any confirmations, and that like the protocol to some degree might be able to resolve it if I think at least 51% are honest, right? Like if the attack is small enough. But if it's big enough, only the humans can step in and resolve it out. But what's important is that like you have clients that can sample a very large set such that their sample always includes at least one honest node. And this is again goes back to the larger full node base you have, the more full nodes you have, the higher the probability of the honest nodes are not eclipsed, because it's harder to partition them, assuming they're well geographically distributed on our different ASNs and the networks and stuff like that, that there's a path between them. That's very important, and that there's a path from the client to the partitions that contain the honest nodes and the invalid ones.
Could we go back for a second? I don't think I completely understand the attack or failure that you're talking about right now.
Let's say all but one node are corrupt, right? So you have 100, you have 1,000, 10,000 nodes, all but one are faulty.
And they're doing what exactly?
They just create an alternative history of valid state transitions. So they do a double stipend attack.
So like all the way back from Genesis or from the latest checkpoint?
No, for the last 10, from whatever, the last like hour or whatever. They submitted some money to Coinbase. Coinbase is the one honest node. Then they reverted that fork and submitted all the money to Binance. And they're trying to run.
So you have a slashable double signing event?
Yes. Yep. So it's slashable, but you need to observe both forks for you to halt.
Right. Okay.
For Binance and Coinbase, right? Like they need to be sampling a very large set such that there is a path between Coinbase and Binance, right? So they're not eclipsed. And as soon as they observe that, hey, somebody in my sample set observed one set signing root A and somebody observed that's exact same set signing root B. As soon as you detect that, you stop confirmations and you're like, the chain is fucked. The majority is double signing forks, so we can't trust it anymore.
To detect this, you only need to be following headers. You only need to be following signed headers,
Correct.
which is very low resources to detect.
Yep. Yeah, this is actually like, but you still need a very large set to guarantee that eclipse attacks are unlikely.
But you don't, if you just follow the headers and the 99% of all the nodes are controlled by a dishonest majority, there's a possibility that they can just propose an invalid state. And because you're only following the headers, you have no ability to differentiate.
So that's a different sort of attack. That's different than the double sign. So now you're talking about like they don't do a slashable double sign, but they do sign an invalid state train. All the people who are in the
it's an extension.
Yeah, you don't need to follow, like the practical application here is that like Coinbase is running a full node, Binance is running a full node, but they don't need to verify all the forks. They verify the fork that they're presented, and then they see a conflicting header. They don't actually need to know anything about the conflicting header besides that the majority double signed, but they have at least one version of the state. Where I think the nuance where we disagree sometimes on Twitter is that for you to know that there's two forks, there's somebody that's providing data in both forks. And if there's a data provider in both forks, that's the one honest node in both forks. So we have the two forks, we have them fully validated, and now humans are going to get involved and it's going to be messy, right? Like Coinbase received 10 million USDC, Binance received the same 10 million USDC. Somebody is going to end up getting slashed, and somebody's going to be short, but it's not a catastrophic corruption of the state where all of the value is lost, right? All the value at rest, all the NFTs in your cold storage, all the tokens in your cold storage, all of those are fine. It's just that transacting amount of dollars during that partition is what's at risk.
So it's about how fast can you be made aware of a short range fork?
What I think is interesting as a thought experiment is that it's a very actually natural process of in practice. Like when you receive a lot of funds, let's say you receive a very, very large transfer, you can actually just simply wait and observe the network, even though it's already confirmed and rooted. Just like in Bitcoin, when you receive a lot of Bitcoin, you should probably wait more than 6 blocks just in case. You don't know if it's an attack. And people assume that because there's electricity being spent on Bitcoin, it's somehow more secure. But what you're actually doing is you're just waiting and observing if there's if the majority of the hash power is trying to screw you or not. Same thing here. You receive a very large transfer. You should probably wait. You should wait to finalize it. And with things like USDC, you could actually confirm that you're in the same partition as Circle, meaning that you and Circle agree on what the view of dollars is at this point. And that's a very strong guarantee that the dollars you're receiving are actually the valid ones. And it's just a natural part of networks, and it goes. It's outside of the actual BFT consensus. It doesn't matter how fast your finality is. There's nothing you can do to make that any faster. It's just should be part of business practices, and it scales very naturally. It doesn't matter what chain you use, if it's Nakamoto or not. So from a very practical point of view, there's no there's no security benefits to more hash power. Like proof of work does not give you anything, even if it's more mathematically elegant. At the end of the day, you got to like kind of cover your bases and do very smart, practical things when you're dealing with very large amounts of money.
Well, I mean, you do get something, which is you can wait to accept the transfer until $1 million worth of electricity has been spent on the chain that you're observing. And then you know that it would cost $1 million of electricity.
But then if you wait on Ethereum or Solana, you can get enough signatures finalizing the block.
You don't know if it costs the attacker that much. Just like you don't know if the attacker in a proof of stake network actually paid for the stake. You have no clue if the attacker in the proof of work network paid for the electricity. It's very unlikely in a stable system that the people that have been running these networks without doing attacks all of a sudden decided to, right? It's very much more likely that there was like some remote code execution bug and all the miners and they did this thing and the attacker did it for free, right? That's kind of the problem is that like the very practical attacks are zero cost to the attacker.
And another thing that we should always bear in mind that if you make an assumption that it costs too much, therefore it's impossible to happen, it's a rationality assumption. And the entire premise of blockchains is that we can't really make rationality assumptions. We always make honesty assumptions. There's a great paper on this called Rationality Self-Defeating in Permissionless Systems by Brian Ford. And it argues that unless the value of the token used, native token of the blockchain, is the highest, it's the most valuable asset in the world, there always is an attack vector that might seem completely irrational from the inside, but is actually profitable externally. So even though some actions might seem irrational to us, the attacker might still benefit in some other way and profit from it.
And some people just want to watch the world burn.
This is probably a good segue into a C-Node, your section on bridges, if you want to take that.
Sure. I mean, we could go into bridges now.
Your call. I was just giving it.
We'll get to the bridges next. Let me ask one other one first. What is economic security? Does the price of a L1 staking token secure the network? If so, should you always settle your high value transactions on the chain with the most economic security?
I would say that there is no such thing as economic security, that it's kind of a false belief. With one-on-one assumptions, there's only valid state transitions, like are accepted by full nodes. So your full node, like in the example that I always give, because it's much simpler to understand, is you have Circle, which is the issuer USDC, and you have your USDC that you own and a private key that you've stored securely in cold storage. Even if 100% of the network is corrupt or the underlying token that secures the network went to zero, there's nothing an attacker can do to convince Circle to transfer your USDC out, your dollars out, without your signature. Your private keys are in cold storage. The attacker can't get to them. The attacker can't break into Circle's infra and mess with their full node. The rest of the network can go completely haywire. And this is like a very beautiful thing. It's what makes these systems truly peer-to-peer. That this like quorum or these like proof of stake networks or hash power networks, that's the message bus to communicate between me and Circle. That like economic security doesn't really exist. There's a much stronger security than that. The economics of the network, what they prevent are like these attacks that could create a double spend. And that means most nodes will detect that there's now two forks and halt. And that's a messy, annoying thing. It would break DeFi, right? Like you can't now process liquidations. The network is effectively down. It's a huge pain in the ass. Let me tell you, like it's not something that you want. But networks can go down for any number of reasons. But that's one of the things that the economics, the Nakamoto coefficient, all of these things that you kind of think about the quorum, what they're maintaining is the liveness and that the system is reliable and can process transactions in a like reliable way. That's kind of my way. I don't know, Toghrul, if you have like a different take on this.
I agree to some degree. I think for the validity of the state transitions, economic security is irrelevant. I think economic security is relevant for censorship resistance. So the more validators you have staking, the more value you have staked, the harder it is for an attacker to actually censor blocks. And another thing that is also useful, economic
Papa,
security is useful for.
I made my own hair clip. Papa, I made my own.
We have another guest on a panel.
Yeah. I think that guess is much smarter. Not wasting time on blockchains.
Yep.
I wouldn't.
Yeah.
So another thing that economic security is useful for is if you're running a light client, you're essentially relying on economic security rather than validating the full state, etc. And one last thing that is also reliant to some degree on economic security, even though at the end of the day it all boils down to social consensus. But like if every answer was just it's social consensus, the whole field would have been boring. So another thing is liveness. So the higher the economic security, the higher the amount of tokens staked, the higher the higher it is to attack the cost of attacking the liveness of the protocol. So it depends. If for correctness,
the cost to create a problem that requires social consensus to recover from.
Yep.
Yeah,
That's basically kind of how I think of it too.
I was going to ask you, would you say that it's the responsibility of the network to make that cost high by design?
I think it becomes high via product market fit. Like the network is doing something useful, enough people depend on it, that kind of cost naturally goes up, unless there's like some infinity minting token bug.
What if you are giving away the resources of the chain for too cheap or for free, and then the cost remains low despite a lot of usage?
The fees, I think at some point the network will be congested then, right? If the costs are too low and there's no dynamic mechanism to increase the fees, then the network will become unusable. That's like a worse problem. I think any network, nearly all modern networks that I can think of have some dynamic fee pricing, some ways to control the number of nodes and the quorum and stuff like that. That if there's like an attack to either stuff one channel or the other, that the costs go up for the attacker. The vast problem with all of these like attack scenarios is that the very likely attack scenarios, the cost to acquire the tokens are free, because you have like a remote code execution in the software. You have some misconfigured, like somebody makes it very easy to launch nodes on AWS, and that thing has like a bug, right? And you have like these like very, very dumb, easy, scalable human things that seem great that have a misconfiguration, and like that's the attack vector. And then all of a sudden, like a very large portion of the network is compromised, and for free, regardless of the economics. Those are the much, much more likely. Like the attacker acquires a whole bunch of nodes, can control a whole bunch of nodes for free, partially or maybe fully. So this is why I think light clients and things like that can sample, maintain a connection to a very wide range of clients in the hopes that at least some of them are the uncompromised, and some of them are configured differently and running different version of the software and stuff like that.
Right. When something is secured by having resources, you have to worry about someone stealing those resources, I suppose.
And with private keys, it's very once you have the private key, you've stolen the resources, and every voting system has to have a hotkey for voting. And that hotkey is responding to automatic requests from packets from the internet. And
you can't use a ledger to vote. Every time you need to vote for a block, you need to sign a ledger transaction.
And have a human in the loop or something like that. That just doesn't work. These are automated systems that sign just the attack surface is enormous. Like it's just like absurd how big it is. So like I think a lot of the cool stuff that Ethereum folks have done in the early days and like to combat this is like building multiple clients, stuff like that. So something that we're focused on as well with Firedancer.
Shall we get into bridges?
Sure.
I understand that you two have some sort of ongoing disagreement about bridges. Could you explain to the audience what exactly that's about?
Do we? We actually
no, we actually
agree.
We agree on bridges, and like the joke is that every month somebody posts, we have a trustless bridge, new trustless bridge coming to ChainX, and it's either me or Toghrul that says, here we go again. There's somebody that is promising a completely like a bridge, a totally trustless bridge. Do you want to explain the problem, or should I? Like why bridges are inherently not trustless?
I can start. You can add any parts that I miss. So first, we need to define what trustlessness is. So from my perspective, trustlessness is obviously doing anything in life requires some certain trust. You have to trust that you exist. You have to trust that things that you see around you are real, etc. So the same with interacting with blockchains. There's no way to interact with a blockchain without having any trust assumptions whatsoever. But how I define trustlessness in the context of blockchains is essentially if you run a full node, that's a trustless interaction with the chain. Anything light clients, anything added on top of it is already not trustless because you add additional trust assumptions that are not there for the full node. Essentially, the bridges are pieces of software that connect independent chains or the chains that have certain dependencies on one another. If we assume that there is a way in which you can trustlessly interact between two chains, then essentially that involves running full nodes for both chains and those both protocols being completely dependent on one another, which just means that it's one protocol. And anything else when you're interacting with a chain that doesn't comply with that definition is by definition to some degree trusted. It can be trust minimized. It can be it can use some form of economic, for example, bonding or whatever, but there's always some trust involved. So for example, even rollups, which are, many people assume that they're trustless. They're not trustless, they're trust minimized. So in case of an optimistic rollup, you trust that there's at least one honest node that is capable of challenging a state commitment. And in a zero knowledge rollup, you assume that the zero knowledge proof system is correct. So even though you're trusting maths, it's still an additional assumption that doesn't exist if you run a full node of the L1.
Yeah, the way that I think about it is going back to that example. I have my cold storage, my USDC keys. Is there a set of keys that are not my own that could convince Circle to spend my dollars? So if I'm holding on the native chain and the L1, like an Ethereum or in Solana, and Circle is running their node securely, and my cold storage keys have not been leaked, there's no other. It's impossible for anyone to convince Circle to wire out my dollars. Now, let's say I bridge them. No matter what that bridge is, I deposit my dollars into this bridge, and then based on some scheme, whether it's economically secured with MPC and a bunch of really cool tech, I get a wrapped asset out, and I hold that thing. That entire system that did the conversion, if that thing is corrupt, they can literally take my dollars, send them to Circle, and get a wire out. And now my wrapped asset is worthless because there's no way I can get my dollars out. And this is true about every bridge. With optimistic rollups, I think it's a much trickier attack vector. There has to be either nobody submitting fraud proofs or the quorum that is running the L1, the Nakamoto coefficient, the Byzantine threshold of nodes is corrupt, which is actually kind of a scary assumption because for most networks, it's actually a pretty small set to get to 2/3. Even though if you have a lot of full nodes, 2/3 of the stake can be, I think, I don't know if it's on Ethereum is under 100. I think it might be 133 on Solana to get to 2/3, 150 or something.
Yeah, it wouldn't be a massive number either way.
Yeah.
The thing is, rollups function under the assumption that the base layer assumptions are correct. So if they're broken, by default, the rollup is broken. So if you assume that there's censorship on an L1, by default, the rollup is broken.
So this is where like economic security is important for rollups. If you have rollups in your system, then the economic security of the L1 becomes even more important.
Yeah, to some degree. I mean, for ZK rollups, the only thing that will basically, let's say, if the L1 is censoring, the only thing that can happen is that your batches are not going to be finalized by the L1. So the worst case scenario is a liveness failure.
Not ZK rollups, like things that require fraud proofs landing on chain. Like what I find really interesting about ZK technologies is you don't necessarily need to build a full generic, fully virtual machine compatible rollup. You can actually just use them in the applications directly. Like you can build a L1 app on Solana that has a ZK proof for very complex computation. It's technically that's a rollup, right? It's like, but no one needs to go around and like pitch it to like a rollup X is running on Solana. It's just here's like a cryptographic, like a state transition that takes like some prover like based output and like does a state transition based on that. That's very application specific to that one thing. So I honestly think that there's a lot of benefit across the entire industry across all blockchains for all the ZK research that's being done, because it doesn't necessarily have to end up as a product in here's like a new ZK rollup that's equivalent to Optimism and is competing with Optimism. That doesn't necessarily need to be the only ways that those products launch.
Yeah, one funny thing about ZK and a lot of use cases, the use cases are not actually ZK. They don't use they're not privacy preserving. They use zero knowledge proofs because they're succinct, not because they're privacy preserving. So, for example, for us at Scroll, we use Halo 2 and we completely removed the ZK part because it just added like 20% overhead, which was completely useless for us.
Since we're talking about ZK rollups, how about Validiums? For a little bit of context, a Validium is a ZK rollup that trusts a centralized committee to publish the data for the state transitions. Once it's initially published, it can be archived and replicated by anyone. What do you guys think about the security properties of these? What sort of use cases they might fall into, or if they're good for anything at all?
Like, if I understand this correctly, it has like basically it's only publishing the state root to the L1, and then everything else is maintained off chain.
Yep.
Is it publishing the updates to the state root onto the L1, or only just only the root update? Can you reconstruct the state root from the L1's ledger?
It would be a rollup then, if it would have done that.
It.
So I think there are certain use cases. So, for example, in a lot of gaming applications, etc., you just don't need the full security. It's not required. And assuming that the committee that stores the data is decentralized enough, I think it's a perfectly fine solution. I wouldn't use it for applications that have tens or hundreds of millions of dollars on them. But also bear in mind that the worst attack vector that can happen is that your funds can be frozen. They can never be stolen. They can just be frozen. Essentially what you can do is if you're a committee that is corrupted, you can freeze the funds and then try to bribe people and ask for like 50% of the money that was frozen in order to unfreeze them.
Why should those games even be on blockchains?
That's a good question.
No idea.
I think that one way where these systems are useful is reducing the attack vectors that like a bridge can do between, like, let's say at Solana and Ethereum. And not only were the headers, like the headers were published, but the ZK proofs that the chains, that this particular fork observed by both chains, assuming there's no majority attacks, are like valid. So in that scenario, you have a bridge that is only exposed to the attack vector that the majority, like quorum on the other side, publishes two roots, and one root is fed to Ethereum, right, and the other root is fed to Binance. But that's a very like expensive attack that requires like basically the L1 to fail a very hard failure, where all the systems that we built in place to prevent that attack have failed, and now it requires social consensus and a user activated soft fork. That's actually, I think, a very good use of that technology, because I think everyone kind of believes that we can prevent that from ever happening. We can actually have big enough networks with enough eyes on them that this idea of the quorum going fully rogue and creating two different histories that are fully committed is impossible. It's not impossible because it's impossible theoretically. It's practically impossible because networks are so used and so watched by so many people that it's impossible to pull off in a practical sense.
One thing to just correct you, what you described is not actually a Validium, because what you described connects to independent chains. So that wouldn't be a Validium. Validium is essentially should be the ordering of a Validium is determined by the base layers, whereas in case of Solana and Ethereum. But the bridge that you described, while that attack is unrealistic, I think for the vast majority of the use cases, I think optimistic bridges are more than enough. To some degree, they provide even better security, because with a ZK bridge, assuming that you finalize as soon as the validity proof is submitted, there can be a scenario where there's a short-term fork. So essentially, the dishonest majority constructed a fork, but never revealed it to anyone. Just submitted it to the base layer of another chain and withdrew some money fraudulently. Whereas if you have an optimistic scenario where you have like, I don't know, 5 hours, a few hours to challenge it, it gives you a window. So essentially, as long as there's at least one person who detected that the validity proof submitted is for the non-canonical chain, you can always challenge and say, oh, by the way, there's another chain there that was built for the same height, and submit the validity proof for that, which will prevent those sort of attacks. So in that case, the only viable attack is a very, very long range attack. So essentially a reorg that spans days.
Are we going to launch a trustless bridge?
A collab on that would be interesting. Yeah.
Folks, I have a quick question. If local fee markets work from a, at scale, and as like demand starts to pick up, is there a reason to have, like these L2s and other sort of like roll-ups and things like this? I guess that's a question for you, Toghrul. Assume they work. Would you still need them? And then the counter question to you, Toli, would be, if they didn't work as well, would you concede the need for L2s and roll-ups?
I think from my perspective, I really like the idea of local fee markets. I think it's a great thing to have, regardless of whether you have roll-ups or not. And they should work. I see no reason why they shouldn't work. The only thing that I have a bit of a reservation about is the UX, because essentially you're not competing with the entire chain. You're competing with like a certain slot, which creates a generalized auction on top of a generalized auction. So assuming that the UX problems are fixed, I think it's a great thing to have. With regards to whether that defeats the purpose of L2s or rollups, I don't think so, because even if you have local fee markets, the node requirements are still the same, which is the main reason why you need rollups. It's the state separation and allowing basically people to run full nodes in an accessible way.
So I kind of agree with Toghrul. Like, I think in Solana, where our premise is like, how do we maximize the amount of like useful information we synchronize and then minimize the cost of the hardware after that? You don't need L2s because the L2s don't help you with that problem. Like, we're not going to synchronize more bits around the world and guarantee that they'll all arrive everywhere at the same time with L2s. So we need fee markets to work. Otherwise, that whole premise falls apart. So I don't see any reason why they wouldn't work, like any engineering reason. And in that system, you don't need L2s from an engineering perspective, unless you're building a market that doesn't actually care about global synchronization. It's a very localized one. And there are markets like that exist for derivatives. Like, you may want to just run a whole pile of derivatives with as low latency trading as possible. And people are mostly kind of just fighting each other, right, on statistical noise. Stuff like that exists. I think whether on a chain like Ethereum, where you've set a upper limit on the cost of the hardware, and then you're trying to work around that constraint, L2s definitely make sense. And I think it's going to be interesting to see is when you have sharding and dank sharding, and you have a rollup that can write to any shard at any time, and that rollup implements its own parallelism and has its own fee markets, like localized fee markets. Do you need more than one rollup? Is that one execution environment enough for all the use cases on Ethereum? And I would agree, and I would say that yes, it's enough, and you don't need any other rollups. And then you can kind of just squish them together and start optimizing both the layers and just enshrine that execution environment directly into the L1.
Just to respond to Anatoly's claim, I don't think one rollup will be enough, purely because you still need to essentially interact with the rollup in real time. You would need, in a trust minimized manner, you would need a full node for that rollup. And essentially, for the rollups, even though we can increase the hardware requirements for them relative to the L1, you would still need to keep them at a certain level. You can't just say, just run a bunch of supercomputers and call it a day. So you would still need multiple rollups at the same time.
Or that one rollup is Solana.
Well, we know that one chain can handle at least the load of Solana. But what if the load was 1 million times higher?
This is actually, I think, philosophical, maybe like an engineering thing based on my experience. You need to put an upper limit on what the expected throughput is, or you're going to design something and miss the mark. You're not going to design for the right thing. Like Google does about 80 to 100,000 searches per second. They're not investing in building a system that does 10 million searches per second, because that's just not what the market needs. They build stuff to make those searches lower latency, right, and to make them higher quality. That's where their engineering efforts are going to. And you have to understand the upper limit of what you're doing. I think it's very likely for the top, 5 nines of valuable transactions in the world to fit in the first 100,000 TPS. That's how Google is, right? I'm sure there's other systems that do search, right? Like there's Wikipedia search and this long tail of things. There's only one Google and it covers the 5 nines of search.
Well, I think that's where this talk of having layer 3s sort of comes from. They're saying a layer 2 is probably going to be enough, but if it's not, we can stack another layer on top.
But the question is, if the world only needs 50,000 TPS, what kind of system would you design? If that was the limit, that's all the world ever needed.
I think it again depends on your requirements. So if you require something that it can be easily be validated, then you would build a system with a bunch of rollups, etc. Going back to the L3 question, I think from my perspective and from perspective of Ethereum as well, I think L3s are inevitable, not because of the throughput. I think throughput for now should be more than enough that all the rollups should be able to handle it, but more for application specific things. So, for example, if you're running an NFT based game, you don't need the composability, and it will be too expensive to settle directly on Ethereum. So why would you do that if you can settle on, let's say, Scroll or Optimism or whatever? Especially for ZK rollups, that's true. If you run L3s, you can amortize the cost of state transition, validity proof verification. So instead of submitting, let's say you have 10 rollups, and if 9 rollups deploy on top of another rollup, then you only need to verify one validity proof on L1. Whereas if all of them settle directly on the L1, we need to verify 10 validity proof, which is much more expensive.
This brings me to another question. Should apps launch their own chains, or will apps inevitably launch their own chains?
I think you're going to see kind of the shift between apps launching their own chains, and then some will become generic, like smart contract platforms, because that's where their product engineers are driving to, and others will become like not want to run the chain because it's a pain in the ass. You saw that with Helium. They're like, okay, we actually care more about radio and stuff like that than we care about running an L1. Let's just use the cheap, fast L1. So a lot of people also make that decision. And it's going to be kind of like, it's going to bisect. But I think any, like the chains that are like become smart contract platforms are going to run into the exact same scalability challenges that everyone is running into. And then they're going to have to make some hard choices, whether they go the Ethereum route or the Solana route.
Or go the Binance Smart Chain route, just crank up the settings and let 50% of the nodes never be in sync because they just can't catch up. I think, again, it depends. So, for example, if you need synchronous composability as an application, you wouldn't launch an app chain, because even if, let's say, you launch it in a form of an app-specific rollup, the composability is in every case is going to be asynchronous. And yeah, so, and I think it's fine to, I don't see an issue with launching an app chain as a rollup or in the form of a Validium, because the engineering complexity is not very much, especially with most of the rollups working on like sequencer outsourcing and prover outsourcing, etc. It's probably going to be just like press a bunch of buttons and that's it. You have a trust minimized bridge. Whereas with separate chains that are secured by their own validators, I think that's just not viable for the vast majority of applications, because you need to incentivize everyone, and it's the cost of incentivizing is much higher than, let's say, a rollup, because a rollup can just be centralized. You don't have to have 20, 40, 50 validators for security. The security is still there. The only reason why you would have decentralized sequencers is for increased censorship resistance, better UX, etc.
Your trading, I think there's going to be technical trade-offs in finality and like latency with the rollups.
It depends on how you do it. So you can, so essentially you can plop any consensus protocol on a rollup and provide economic guarantees. So essentially it would be a side chain until the rollup is settled on the base layer. So let's say in a hypothetical scenario where Solana becomes an Ethereum rollup, until Solana settles on Ethereum, you rely on Solana's security. And then once it settles on Ethereum, you rely on Ethereum's security.
Sure, but then you're basically running a full chain, or you're limiting security. So if you only run one node, you have to put up capital, presumably, to secure that one node. And it's also like, you're very likely to like stumble into like money transmitter and a whole other things, like requirements, like when you're dealing with like regulation, if you're running that one node, that's bonded to guarantee that there's like that this thing isn't gonna screw you.
It depends on the application. So let's say if it's a game, then you're not a money transmitter. It doesn't matter. Yeah, if you're processing payments and stuff like that, obviously you shouldn't be run a centralized sequencer, because then you can get into legal trouble, etc. It's better to have it decentralized.
The problem with like anything in crypto, even if it's a game, as soon as it's connected to an L1, it can be traded. So you're transferring value. So you're basically like, you kind of have to assume that you need the security that you would for payments application or anything else. That's kind of the rub here. Unless it's a totally like off-chain system where the data is controlled by that like one network and they can shut it down at any time. As soon as you get into like true like digital ownership, like the users own the value, you're handling transfers of value. So you need to start providing security. And this is like, then you're like down that rabbit hole. How do I provide security? Right? Like, it's a whole lot of nodes.
No, I mean, if you're bridging and you're transferring value between the bridge, yeah, but you can also come up with a hypothetic game that is essentially siloed from the rest of the ecosystem and just uses the underlying base layer for security, for settlement, but it's still completely siloed.
But what is that game transferring? Is it items owned by the users, like true digital items? If it's not, then it can just run a database. Doesn't even need to be a Web3 game. Like then, like why not use AWS?
I mean, if you ask me, I think the majority of the on-chain games can just run as an AWS instance. They don't really need to be on-chain. But I think you could come up with hypothetical games or certain applications that would be applicable to this scenario.
I think it would be a very small. I can't think of any, like out of the gaming folks that we talked about gaming, the gaming applications all have like some NFT integration where there is like transferring NFTs or in-game value. And those transfers have to go through some secure system, like either a decentralized one or a regulated centralized one. There's just kind of like no way around it. But if it's a game that doesn't have the digital user-owned digital items, like it can run on a database. It is really not a Web3 game at that point. So like
an example would be Dark Forest. I'm not sure if you've heard about it.
So that's where you're just kind of earning achievements. There's no value transfer.
Yeah.
Could Dark Forest go on AWS, or is the ZK stuff involved in that game? Like, does that need a blockchain?
You could run it within a single node on AWS. Yeah. You can boot up a single node, like a testnet, and run it. But there, like, I think people want the provenance of this occurring on mainnet, and like that has intrinsic value to the user. But that is actually an interesting application. You're like creating a lore or like historical record artifacts on chain that are not necessarily like valuable items. That was one of the use cases that we thought for proof of history was like recording events, just creating like a history of the world where you have guarantees that event A occurred between event B. But I don't think there's any value. I don't think there's like any value to that.
What wasn't Namecoin basically created with the original idea of Namecoin was similar? Then
I'm not sure. I
Essentially,
don't remember Namecoin.
it was one of the first protocols built on top of Bitcoin. Essentially, it was like a name registry for Bitcoin.
Oh, that's right. That's right.
That's the end of my questions for the two of you, but I have some like per individual questions if you want to go through those.
I mean, I think we're at the end of the hour and 20-minute schedule, and we're going to have a hard time editing this episode.
Okay.
We might, but look, I mean, we're down to make this a regular feature. If you folks have time, once in every 2 or 3 months, as new conversations emerge on Twitter or otherwise, and we'd love to have this be a feature.
As long as it's not at 5 a.m., I'm happy to join.
Yeah.
Well, it's 6 a.m. for Tanmay as well. So thank you two gentlemen for joining early.
All right. I can stay up late, do it at 10 p.m. So it's a little easier for you guys.
Gentlemen, thank you so much for doing this. Cnode, big special thanks from our community to you for agreeing to moderate it, put so much preparation into the questions. Appreciate your help with hosting this. Thank you, Toghrul and Anatoly. We'd love to have you all back. Really appreciate the civil debate on the show.
Great. Thank you, guys.
Thanks so much.
Thanks for having me. Thank you, Connor, for putting the questions.